So let's take a look at section 7.2, and in this section we're still talking about surveys and how we measure the quality of a survey. So that's the name of the topic for the section, is measuring survey quality. So when we take surveys, we conduct polling data, how good is that poll? There's some different things we want to look for. So first of all, there's two terms we want to kind of keep in mind as we go through this section, using accuracy and precision to measure the quality of a survey, describing the important features of what's called a sampling distribution, including something called the standard error. Okay? So it says evaluating surveys. Statisticians evaluate the method that's used to conduct a survey. So how the survey is conducted is really the most important thing. And when you hear people talk about polling, like in the presidential election, and how certain polls are looking, the survey of the quality is always judged by the method that they used. And in this picture over here, we're looking at 4 targets, I guess, and they're kind of giving you an idea of what we mean by precision and accuracy. So the goal, accuracy and precision. An estimated method should always be both accurate and precise, as close as we can get it. So accurate, the method measures what it intended, and it correctly estimates the population parameter. And sorry, I'm a little bit short on room here. Let me write that below it. The population parameter. Remember, parameter is a measurement on the population, for example. So like think about an election. If we want to know what proportion of a population is going to vote for a certain candidate, that's the population parameter, the proportion. And that's what we're intending to try to estimate using our survey. So how accurate it is, how well it estimates the population parameter, and precision. So what we mean by precision is if we were to repeat the method, if we were to conduct multiple surveys using the same method, the estimates are very consistent. So think consistency. The closer the polls are to the value that they get, the more consistent they are. And that's what we mean by precise. So in this little picture here, you can see in the upper left corner, it's low accuracy and low precision. Low accuracy because none of them really hit the target, and low precision because they're kind of all over the place in this picture here. In this picture, it's low accuracy because it's not near the target, but it's very precise because they're all close to each other. The next one, it's high accuracy but low precision because, again, they're all over the place, but they're all pretty close to that target. This is what we want to aim for, right? We want to be similar and we want to be close to that bullseye as possible. All right, so let's look at an example here. So this is a simulation, and we're going to look at some different simulations in this section. And we're looking at a generic, just a simulated 5K run. So we've got a small population here. Only 8 people are participating in this 5K. Of those 8 people, we know that 2 of them are walkers and 6 of them are runners. We're going to randomly sample 4 people at a time from this population. So make sure that you're thinking about what all these terms mean. We're going to take a sample, a random sample of 4 people, and we're going to calculate in those samples the percentage of walkers for each sample. So it says, note, P equals 25% for the population are walkers. What does this symbol mean? This is really important, and we had this in the last section, so I really want you to remember this. P is the population parameter, and what is it? It's the proportion. What do we mean by proportion? The percentage or the fraction of people who are walkers. So the proportion, in this case, it's the proportion of walkers, and it goes with the population. So P, remember, is for the population. P hat, which you're going to see down here, P hat is the proportion of walkers, so the proportion of walkers for the sample. So P hat goes with the sample. P, remember, goes with the population. Let me add that up here. All right. So the population parameter in this case is 25%. The population parameter, that proportion does not change. There will always be 2 out of 8 walkers in this population. That's not going to fluctuate. The population parameter is what it is. It doesn't change. The question, though, is will each sample, if we randomly select it, contain 25% walkers? Is it possible to get a sample with no walkers? Is it possible to get a sample with more than 25%? Not in this case, but because we only have 25% for the entire population. But is it possible to get a sample with no walkers? So let's take a look. So using StatCrunch, we randomly pulled 3 samples of 4 people each. And so let's assume this is what we got. So our first sample contained 25% walkers. Notice the notation, p hat, because it's the sample we're looking at. So 1 out of 4 in my sample were walkers, so that would be a proportion of 25%. In the second sample, I got 0 walkers. And in the third sample, actually I misspoke earlier, I said we can't get more than 25%. We can because there's 2 walkers in the group, and I'm only taking 4 in my sample here. So in this case, I got 2 out of 4 who were walkers, so that gives me a p hat value of 50%. What I want you to notice here is that the sample proportion changes from sample to sample. Samples are going to fluctuate. The proportion of walkers I get is going to fluctuate with every sample that I pull. In a survey or a poll, it's going to be the same thing. The proportion of people who say they're going to vote for a certain candidate, that's going to fluctuate from one sample to the next. But the population proportion never changes. That's always going to be 25% here. So this table below just kind of summarizes what we've got so far. In the first repetition, we had p hat of 25%. In the second repetition, we had p hat of 0. And in third repetition, we had p hat of 50%. Again, notice the population parameter does not change. That's not going to change at all. All right. So what we've done here is we've created what's called a sampling distribution. So the sampling distribution of p hat, we can think of this as an important term. This is the probability distribution for our sampling proportion. So for p hat. So the probability distribution of p hat is called the sampling distribution. And sorry that's so messy. Sampling distribution. All right. We can represent this using a table or a graph. So remember in chapter 6 we talked about a probability distribution. That's basically what this is. It's a probability distribution for our sampling proportion. All right. So the possible values for p hat were 0, 25%, or 50%. The probability of getting each of those values is in the table here. Now, I'm going to make a little note here. Don't worry about where I'm getting these values from right now. So don't worry about these numbers, because this is not the important thing to focus on. The important thing I want you to get out of this table is that we had 3 different possibilities for p hat, 0, 25%, or 50%. So those were our possible outcomes. And then the probabilities next to them are provided. And also notice that if you take these numbers and you add them up, they would add up to 1. And they should, because remember, an entire probability distribution, all the probabilities have to add up to 1. And I've just got a little note here because I want to keep reminding you of this. What does p hat represent? Remember, p hat is the sample proportion of walkers. If we were to put this on a graph, so the probability table above, probability distribution above, we were to put this on a graph, here's what this would look like. Make sure you see. So I had 3 possible values, 0, 25%, or 50%, and there's the probabilities of getting each one. So there was a 21% chance from here of getting 0. There's a little over 57% chance of getting 25% walkers, and then a 21% chance of getting 50% walkers. And it says, why are 0, 25, and 50 the only possible values of p hat? Why is that true? Because in our original sample, remember we only had, strike that, in our original population, remember that we only had 2 walkers in the first place. So I could either get 0 walkers in my sample, which would be 0%. I could get 1 walker in my sample, which would have been 25% of the sample, because remember there were 4 in the sample, 1 out of 4 would be 25%. Or I could get 2 walkers in my sample, which would have been half my sample, or 50%. Is it possible to get 100% in p hat for our sample? No, since there were only 2 walkers in the population, in the original population, okay? Then it says, what is the mean of the sampling distribution? So if we wanted to compute the mean, I'm going to use x bar here for mean, and I'm going to do x bar, I'm a little p sub hat just to remind us here. So this is going to be 0 plus 25 plus 50 divided by 3. and that gives me a value of 25. And notice that 25% is the same as our original P. Remember, in our original P, our population proportion was 25%. So a few notes about our simulation here. Our estimator, P hat, is not always the same as our parameter P, right? It could have been 0 or it could have been 50%. The mean, however, of the sampling distribution is 25%, which is the same as the value of P. So what does this indicate? This indicates that our estimator is what we would call unbiased. And there's a lot of theory behind where this comes from. Don't worry about any of that right now. Just kind of take my word for it. So if the mean for the sampling distribution is the same as the true population parameter, that means that our estimator is unbiased. Even though P hat is not always equal to P, notice that the estimate was never more than 25% away from P. And the next thing I want to mention, a new term here, is called the standard error. So the standard error is basically the standard deviation for our sampling distribution. So we remember what standard deviation is. That tells us how much each, if we're looking at a sample of data, the regular standard deviation tells us how much each data point varies distance-wise from the mean. So the standard error kind of acts the same way. It gives us a measurement of how much our estimator varies. Remember, standard deviation measured variation. Standard error does the same thing. So it tells us how much our sample varies from sample to sample. Remember, every sample is going to be different. There's always going to be variation among our samples. The idea, though, is that we want that standard error to be small. So when the standard error is small, we say that the estimator is precise. Remember that term we had earlier, precision. That means that we want the consistency from one sample to the next. We want the variation to be small. So that means we want our standard error to be small. All right, let's see. What the next line here is bias. So bias is measured by the distance between the mean, or the center, of the estimator for P hat and the mean of our population parameter P. So generally speaking, we want the bias to be small, or 0 if we can get it, or as close to 0 as possible. So close to 0. That's our goal, because that indicates we've got more accuracy in our sampling procedure. All right, let's look at another simulation. So this time we're using the same 5K example where we have walkers and runners, but now we're looking at a larger population. So now we're considering a population of 1,000 people in our 5K race. So among those 1,000 people, 250 of them are walkers. Notice that that still means that P, remember what P was, keep reminding yourself this, P was the population proportion, so P would still be 25%. Walkers, right? 250 out of 1,000, 25%. We're going to take random samples. This time we're going to use samples of size 10 instead of just 4. And we're going to find the sample proportion P hat for each sample. So I've done this in StatCrunch. You're not going to have to know how to do this yourself in StatCrunch, but I want to just give you an idea of what this picture would look like. So in StatCrunch, what I've done is I've pulled 10,000 samples. So I've just pulled a sample of 10, sample of 10, sample of 10, over and over again, 10,000 times. And then I've graphed the results in this picture. All right, so what happens? Well, I had samples where I had 0% walkers this many times. So this is a histogram, right? Looks like it's around 500, maybe a little bit over 500, okay? I had 10%, or 1 out of 10 in my sample right here. 20% of my sample was walkers, was up here. And then 30% of my samples for walkers was here, and so forth. This time, because I can have up to, my entire sample can be walkers, right? If my sample is 10 people and there's 250 walkers in the population, I could have anywhere from 0 to all 10 this time could be walkers. And so that's what this histogram is telling you. All right, so let's make a few notes here. N is 10, and this time we're looking at 10,000 samples. Since the center of the distribution, so the center of the distribution is noted by this little arrow right here, the center of the distribution of p hat is about 25%. So what does that tell us? That the bias of p hat is 0. Okay, remember we want our bias to be small. We can have it be 0. If the bias is the same, or I'm sorry, if the center of our sampling distribution is the same as the population proportion, then that means the bias is 0, even though we have a larger population and a larger sample size used. All right. However, the variation, so the variation of p hat is less than it was in our previous sample. How do I know? Look at the bars in my graph. They're closer together than they were in the previous graph. Let me show you real quick what the previous one looked like. Back here, we only had 3 options and they were pretty spaced out. Do you see what I'm talking about? So there's, visually speaking, there's less variation in my graph this time from left to right than there was in the previous graph. So that means there's less variation in my sampling distribution. So what does that tell us? That the estimator is more precise, even though the population that we used is larger. So in general, the precision, how precise we are, so the precision has nothing to do with the size of the population. Instead, it only has to do with the size of the sample. And the sample size is going to get really important here throughout this chapter. More and more we're going to talk about sample sizes. So a sample size of 10 produced less variation than the sample size of 4, regardless of what happened with the population. What sample size would produce even less variation? So I pulled sample sizes, remember, of n equals 10. What would be better? Larger samples. Larger sample sizes are going to produce less variation. So anytime we can use larger sample sizes, the better off we're going to be in terms of variation. So larger sample sizes mean less variation. And we're going to look at this simulation one more time with a sample size of 100 in the next video.